Alright, now for the last part right here. So I wanted to go over these ones right here. So determine convergence or divergence using all the tests listed: the nth term test, direct comparison, limit comparison, and integral test. So one for each problem. So yeah, I set this up where mainly you use one of these for each. There might be some where you can use one or the other. I don't think so, but at least I set it up where ideally you would use one for each. So I'll try and explain the best way that I can, how you can potentially tell. Um, for the first one, um, uh, I'll use the integral test for the first one. So the reason why I wouldn't use it on any of these is because for nth term tests work out really nice. Say for like number 8, where if I analyze the numerator and denominator, I see polynomials and of the same degree. So that way, I know when I take the limit of this, it's not going to be equal to 0, which means the nth term test is really good because you want in the nth term test, you want the limit as n approaches infinity of your sequence to be not equal to 0. So that's why I'll use the nth term test here. This one, direct comparison. I'll explain why when I get there. And this one, limit comparison, because again, I'll explain when I get there. So, in any case, I don't really see polynomials on top and bottom here. I have a natural log function, um, and I don't see something that looks similar to a Maclaurin series, which is the case for number 9. And I don't see something similar here, which looks like it's going to be a p-series for number 10. So that's why I say the integral test for this one right here. So from using the integral test, then I'll use the limit as n approaches infinity. We'll do from 2 to n of 1 over t times the natural log of t dt. So the integral test says that if this limit right here converges, the series converges. Or if this integral diverges, then this series diverges. So both the integral and the series will converge or diverge depending on the integral. So let's use an antiderivative here, but in order to use this, I'm going to have to use u substitution because I see this product right here, and I know that the natural log of t, if I use the natural log of t as a substitution, I know that I'm going to get t as a derivative, which will cancel out. So say u is equal to the natural log of t, then du is equal to 1 over t dt, and dt is then equal to t du. So if I use my substitutions, so the limit as n approaches infinity, I have the integral from 2 to n of 1 over t times by u, and then t du, and you can see that the t in the numerator and t in the denominator will cancel. So I have the limit as n approaches infinity, and then we're going to have the integral from 2 to n of 1 over u du. Now let's integrate with respect to u. The antiderivative of 1 over u is going to be the natural log of u. So I have the limit as n approaches infinity of the natural log of u as the antiderivative, and this is going from 2 to n, and now we have to undo our substitution. So the limit as n approaches infinity, and we're going to have the natural log of u, which is the natural log of t. This is from 2 to n. Let's evaluate our bounds. So we have the limit as n approaches infinity. We're going to plug in n. That's the natural log of the natural log of n. And then minus the natural log of the natural log of 2. And as I apply my limit now to as n approaches infinity, this will be infinity, that will be infinity, this will be infinity. So this is going to be equal to infinity. If it's equal to infinity, that means the area from 2 to n of this function right here is infinite, meaning you can't find the sum of that area. It diverges. Therefore, the sum of the series also diverges. So both diverge. Okay. Diverge. Alright, so for the next one. So for this one right here, I'm going to use the nth term test because the leading term's right here. So the nth term test says if I apply the limit as n approaches infinity of my series, in this case 4n squared minus n cubed divided by 10 plus 2n cubed. Well, if this does not equal 0, then it diverges. So let's show that it does not equal 0. Well, if I plug in infinity, I get infinity over infinity, so use L'Hopital's rule. I get indeterminate form, so L'Hopital's rule. Then this will be equivalent to the limit as n approaches infinity of 8n minus 3n squared divided by 6n squared, which is equal, again, if I plug in my bounds, I'm going to get infinity over infinity, so I'm going to need L'Hopital's rule again, and that's going to be equal to the limit as n approaches infinity. That's going to be 8 minus 6n divided by 12n. And then one more time, L'Hopital's rule, I'll need it again. This is going to be the limit as n approaches infinity of negative 6 divided by 12, which is equal to, this is going to be equal to negative 1/2, which does not equal 0, so the series diverges. So the series diverges. Just keep in mind that the nth term test can only prove divergence. It cannot prove anything else. So if this was equal to 0, it means absolutely nothing. It could still diverge or it could converge, but you're not going to find that out by using the nth term test. Got to use something else. Okay, for this next one, so this one right here, I'm going to use the direct comparison test. So the reason why I want to use the direct comparison test, well, if you remember up here, we had this series of e to the x, and e to the x, so this is the Maclaurin series. It's the series as n equals 0 of x to the n over n factorial. So if I paste this here, I have this right here. Now this could look very similar to this if I have e to the x to the 4th. So that would be equal to the series as n equals 0 of x to the 4 n divided by n factorial. Now, the reason why we want to use this is because according to the direct comparison test, what you want to do is you want to take a series that you know, in this case a Maclaurin series. Now we know this series right here, if you remember from the Maclaurin series, that this series converges for all x, for e to the x. So this is equal to e to the x for all x. Okay, that means this one also converges to this e to the x function for all x. Now, we also know that this series right here has to be greater than this series at any term greater than or equal to x to the 4n divided by 2n factorial plus 1. The reason why I know that is because they both have the same numerator. So that means that at any n equals whatever, so n equals 0, n equals 1, numerator is going to be the same. But at n equals 1 or n equals 2 or so on and so forth, this is always going to be a larger denominator because it's 2 times by n factorial and you're adding 1. So if you have a larger denominator here, you're dividing the numerator by a large number, meaning this term is smaller. So because I know this right here, because I know this converges, and for every single term from n equals 0 to infinity, this term will be greater than that term, and this converges. therefore this converges because it's small. Every term is smaller than that. So by the direct comparison test, let's see if I can make the wording a little bit better. So let's say x to the 4n over n factorial converges for all x, and x to the 4 and the series of x to the 4n over n factorial from n equals 0 to infinity is greater than or equal to n equals 0 of x to the 4 n divided by 2n factorial plus 1 for all n. Therefore, the series converges for all x values, just like these other functions that we use, or other series that we used. Okay, so that's direct comparison. Now, limit comparison has 3 different outcomes, but there's really one outcome that happens, like, I feel like 90 to 100% of the time. But the limit comparison, let's see, do I have a, yeah, 10.5 notes. Let's see if I bring this back up. Okay, so here are the results of the limit comparison. So b sub n is usually your comparison function. So first of all, a sub n and b sub n have to be greater than 0 for all n. So there's that condition. And if you know b sub n, so b sub n, you should know b sub n if it converges or diverges. That's another thing you should know. And if you apply the limit as n approaches infinity of the ratio of the two series, if it's equal to something between 0 and infinity, then a sub n and b sub n both converge or diverge, depending on what you know about b sub n. And here are the other ones. So if it's equal to 0, so if it's equal to that lower bound, then then a sub n will converges if b sub n converges, and then if you get this one up here, then b sub n diverges and b sub n diverges, then a sub n diverges. So these are the only 3 possible outcomes you can get when using limit comparison, but this one happens most of the time right here. So, which is what we like. So with that being said, let's so what do I want to compare this with? Well, I want to compare this with something that's similar to the function, that's similar to the expression itself. So in this case, if I use the series n equals 1 from 3n over n cubed, which is equal to the series n equals 1 from 3 over n squared. So what we know from what we learned in 9.3 is that this is similar to this right here. And we know that this converges. So it converges by p series. And p is greater than 1. So with that being said, so let's run the limit comparison test. So the limit as n approaches infinity of 3n plus 2 divided by n cubed minus 2n, and then divide it by our comparison series. So that would be that right there. Okay, so then this would be equal to the limit as n approaches infinity. That would be 3n cubed plus 2n squared divided by 3n cubed minus 2n. And through L'Hopital's rule, if you keep going through that, you're just going to get 3 divided by 3. Well, you'll get a ratio, 3 divided by 3, which would be 1. So this limit is going to be equal to 1, which again is between 0 and infinity. So our limit was 1, which is between 0 and infinity. So both of them converge or diverge depending on what you know about b. So in this case, since we know that B converges, so the other one converges. So by limit comparison tests, both converge, including the series that we're given right here. Okay, so there's 4 tests right there. All right, telescoping series. So for this one right here, you're probably going to want to use partial fraction decomposition. Do you always have to use it? No. But for the sake of the test, I'll probably just make it so you do. So using partial fractions, we'll say this is equal to a over 4n minus 1 plus b over 4n plus 3. And by using the least common denominator and multiplying, you're getting rid of your denominators, you'll get 7 times by a, and you'll have 4n plus 3 plus b, and then you'll have 4n minus 1. Okay, so let's say we let n be equal to 1 divided by 4, so positive 1 over 4. Okay, in that case, we'll have 7 is equal to, this is going to be gone, and then we have to plug 1 over 4 here, so if I plug in 1/4, that's going to be 1 plus 3, so it's going to be equal to a times by 4, and so a is going to be equal to 7/4. Okay, so let's get rid of the other one. So if I come here, let's let n equal negative 3 divided by 4. That way that would be 0. So negative 3 divided by 4. We'll get 7 is equal to, that's going to be 0. And if I plug this in here, that's going to be negative 3 minus 1. So this is going to be a times by negative 4. And so b, what am I doing? That should be b right there. So b will be equal to 7 divided by negative 4. So my series, if I write it with my partial fraction decomposition, it's going to be equal to, so this would be 7 divided by 4 times by 4n minus 1, and then minus 7 divided by 4 times by 4n plus 3. So my next thing that I'm going to do is make a list of partial sums so I can see what's happening. So my first partial sum, so if I plug 1 in here, I get 7 over 4 times by 3 minus 7 over 4 times by 7. Okay, yeah, I think that sounds good. We could simplify that, so that's equal to 7 over 12 minus 7 over 28. So that's our first partial sum. Our second partial sum would be equal to the same thing that we had, so 7 over 12 minus 7 over 28, and then plus, well, if I plug 2 in here, I'll get 7 over 4 times by, now if I plug in 2 here, that's going to be 8 minus 1 is 4 times by 7 is going to be 28. Minus 7 over, so if I plug in 2 here, that's going to be equal to 8 plus 3, which is 11 times by 4, so 44. And so this is going to be equal to, you can see here, that those two are going to cancel out, so you'll have 7 over 12 minus 7 over 44. And if you continue the process, you'll discover that the inside terms will always cancel, thus making it a telescoping series. And so the only term that stays is this term right here, and this term always gets smaller. So you can sum that up with the nth partial sum is just going to be 7 over 12, then minus this last one, as in the first two partial sums and as in every partial sum afterwards, it's just going to be the nth term of this right here. So 7 over 4 times by 4n plus 3. And if you apply the limit as n approaches infinity of your partial sums, well, first of all, that's how you find a sum anyways in the first place. The sum is equal to the limit as n approaches infinity of your list of partial sums. and that would be, so as n approaches infinity of this, this goes to infinity, so you have 7 over infinity, which is 0, so you're just left with 7/12. So that right there is your sum of your telescoping series. Alright, let's finish this up right here. So find the interval of convergence of the series and state the radius. If the interval is not all real numbers or the center, test the endpoints for convergence, absolute, conditional, or if they diverge. Alright, so to find the interval, you use the ratio test. So the limit as n approaches infinity of the absolute value of x minus 7 to the n plus 1 divided by 2n plus 2, if you plug in n plus 1 for this right here and multiply out, factorial times by, this will be 2n factorial divided by x minus 7 raised to the n. And if you simplify that, well, this is going to be x minus 7, okay, times by the limit as n approaches infinity. So 2n factorial and 2n plus 2 factorial. So one thing to know about 2n plus 2 factorial is 2n plus 2 factorial would be equal to 2n plus 2 multiplied by 1 less than that, and 1 less than 2n plus 2 would be 2n plus 1, times by 1 less than that, which would be 2n, and then times by 1 less than that, and so on and so forth. So that would be times by 2n factorial. So considering that that's what 2n plus 2 is equivalent to, you can see that we have a 2n plus 2 on the numerator, and we have a 2n plus 2 on the denominator, which would cancel out. So I'll be left with 1 over 2n plus 2 times by 2n plus 1, which I don't really need to FOIL out, because if I let the limit go to infinity, I have 1 over infinity, which is going to be equal to 0, and 0 times by x minus 7 is still going to be equal to 0. And if the result of a power series ratio test is 0, then the series converges for all x values. So the series converges for all x. Okay, so there's no interval to check for because it's all real numbers in x. Alright, so let's go to this one. Let's find its interval. So we'll use the same test. So the limit as n approaches infinity. Absolute value will have n plus 1 factorial divided by 2 to the n plus 1. And then we'll have x to the 2n plus 2 multiplied by 2 to the n divided by n factorial and x to the 2n. Okay, so this right here will result in x squared. So it's going to be x squared on the outside times by the limit as n approaches infinity. Okay, so the limit as n approaches infinity, this is going to be equal to 1/2. So I know that I'm going to have a 2 in the denominator, and then this right here is going to be equal to n plus 1, and that's everything. So if I apply the limit as n approaches infinity, that's going to be equal to infinity times by x squared, which is infinity. And by the ratio test, if your power series is, by the power series, your limit is infinity, then the series converges only at the point, only at the center point. So the series converges. In this case, the center is at x equals 0. I can tell because there's nothing like that. In this case, the center is at 4. Let's see up here. You can tell the center is at 7 right there. So that's how you could tell. So in this case, the series converges at x equals 0 and only 0. Okay, so no interval there to be worried about. And then here, so we'll run the limit as n approaches infinity of the absolute value. We'll have x minus 4 raised to the n plus 1 divided by the square root of n plus 1 times by the square root of n divided by, we'll have x minus 4 raised to the n. Alright, so this is going to give me x minus 4, so x minus 4, then we'll have the limit as n approaches infinity, and we'll have the square root of n divided by n plus 1. And here I can divide every term by n. That will make my limit a lot easier to solve. So then that would be equal to x minus 4. We'll have the limit as n approaches infinity of the square root. That's going to be 1, because if I divide by that by n, it's going to be 1, and then 1 plus 1 over n. And if I allow the limit to go to infinity, this is 0. We have the square root of 1, so it's equal to 1. So equal to x minus 4. So this is what my limit converges to. And if it is less than 1, then it converges. So there you go. So with that being said, my radius is equal to 1, and my interval, so what is it asking for? Find the interval and state the radius. So there you go. So my radius is equal to 1, and my interval is going to be from x is less than, let's do negative 1 there, so that's going to be 5 and 3. Okay, so there is my interval from 3 to 5. And now we just need to test our endpoint. So let's say we have x equals 3, and we'll test x equals 5. So if I plug 3 into my series right here to see if it converges at that point, we'll get the series as n equals 1. If I plug in 3, that's going to be equal to 3 minus 4 is negative 1 to the n divided by the square root of n. Now, square root of n is n to the 1/2 power. So, n is less than 1, so it's a p-series. And this is a p-series that will converge. So we'll run the, just to verify, the alternating series test. Okay, so the alternating series test, it says that if you take the non-alternating part, so in this case 1 over n to the 1/2, 3 things have to happen. So 1, all positive. So in this case right here, the series, so if you start at 1, this would be 1 over 1, and if you keep counting each term, the series always has to be positive, so we're good there. Okay, 2 has to decrease for each term, and that is going to be the case. So as n equals 1, this is always going to, the denominator will always increase, therefore the expression will always decrease, and it has to decrease to 0. So the limit of all the terms, so if you count the terms to infinity of a sub n, it has to be equal to 0. So that would be the case, because if you apply the limit as n approaches infinity here, it's going to go to 0. So by the alternating series test, this is a convergent, this series right here converges. However, the absolute value, so the absolute value of this series, we'll say of a sub n, is equal to the series of 1 over n to the 1/2. Now the series itself is a p-series, and this diverges. So we can only say that that it converges at x equals 3 conditionally, and that is only upon the condition that this is not the absolute value will it converge at x equals 3. So at x equals 3, it's conditional convergence. Convergence. Okay, and then x equals 5. Let's go ahead and give this one a go. So we'll apply the series as n equals 1. And if I plug in 5, I get 1 to the n, which is 1, divided by n to the 1/2. And again, by p-series, this is a diverging series. So this diverges by p-series, where p is less than 1. So diverges by p-series. Okay, so I think we've covered all the bases of the question. So we found and for all of these we found the radius and interval as needed. And if it was an interval, like in this case right here, then we test the center points and we found if they converge, and x equals 3 converges conditionally, and here it diverges by the p-series. Okay, that should cover everything for the test, honestly. I plan on following very closely to what I have on the practice test, and so I hope it helps you guys. Let me know if you have questions.